A semaphore is a synchronization mechanism. So synchronization allows two or more processes or threads to communicate in a useful way. Specifically, a semaphore consists of an integer variable s and a queue named q of processes or threads. So Q is a queue of processes or threads, and S is an integer. Now, when the semaphore is initialized, S must have a non-negative value, and Q will start out empty. Now, there are two basic operations on a semaphore, and these are semWait and semSignal. The purpose of semWait is to tell the currently running thread to claim control of a resource and make it wait if that resource is not available. The purpose of semSignal is for one process to tell other processes that it is done using a resource, and therefore that resource is now available to use to any process that is currently waiting for it. Now, the specific mechanics that make these high-level ideas possible are the following. semWait decrements S. Additionally, if decrementing S causes S to now be negative, then whichever process or thread was running when this command was executed becomes blocked. Specifically, it is placed into the queue Q. So the collection of processes in the queue are those that are waiting for some resource to become available. Signal causes S to increment. If after the increment S is less than or equal to 0, then that means there are still some blocked processes in the queue, and one of them becomes dequeued and unblocked and is thus able to run. Now, if the queue Q is a first in, first out queue, then that means this is a strong semaphore. Otherwise, if we don't have any guarantee about the order that processes are released from this queue, then we say this is a weak semaphore. Now, given all of this information, the way to interpret it is the following. We initialize S to a non-negative value, and we're essentially saying that S is the number of instances of a given resource that are available for processes or threads to use simultaneously. S decrements every time one process claims a unit of that resource. Eventually, S gets decremented to the point where it is negative, meaning that all future attempts to claim that resource cause a process or thread to become blocked. Whenever a process or thread is done using the resource, it must use the semSignal command so that the waiting processes will know that they can now take a turn at using the now available resource. This code provides a high-level example of how you might use semaphores to achieve mutual exclusion in a program. Mutual exclusion is when certain processes are allowed to access a given resource at a time while excluding access to that resource from other processes. In particular, if you have multiple processes running, then there will be some critical section in the code of each process which cannot be executed across all processes at the same time, at least not safely. The semaphore is what bounds this critical section to provide you with mutual exclusion. The idea is this. So this is pseudocode, and we have this process here. This is essentially a function we've defined that is the code that will be running in each of our individual processes or threads. Now, the actual start of the program is here. We have a main function, so we launch this program, we run the main function, and this command par begin is executed, and this is a simple pseudo command that means parallel begin. You'll see that when we are actually launching multiple processes using pthreads, the code is a bit more complicated. But for our pseudocode, we assume we have a very nice, clean command, and what it does is it launches the function command process with a parameter of 1 as one process or thread, and it launches the command process with an argument of 2 in another process or thread, and so on up to process n. Now n is a global integer that is defined as the number of processes we want to have running at the same time. So after this main function executes, we have one process running one copy of this code where the value of ID is 1. We have another process running another copy of this same code in parallel where the ID value is 2, and another with 3, 4, 5, and so on up to whatever n is. So we have multiple copies of this exact same code running at the same time. Now what does this code do? So this code has an infinite loop that keeps performing some work that is the critical section. Now this is for a model of computation where we have these processes running forever, but of course you may launch processes or threads that are meant to do a little bit of work and then exit and finish. So this while true may not be appropriate. But it is often the case that if we have multiple threads running, we want them all to keep doing work until some greater goal is accomplished or until the program is simply terminated. So we have each of these programs running an infinite loop, and the critical section is some code that actually does something. Here I've just put a comment and not actual computation here, but we could be accessing a shared buffer or a shared file or some other resource that we can't have all processes safely messing around with at the same time. So that's what makes this the critical section. We bound this access to the critical section with a call to semWait and a call to semSignal. So let's say that inside of this critical section of the code, we both access and sometimes change the value of some global variable that all of the processes want to manipulate. So I've defined a semaphore S to be initialized to the number of available units of a resource. So S is basically the integer part of that semaphore description I provided earlier. So let's say that we're accessing a file and only one process should ever access the file at a time. In that case, S would be initialized to 1. Then we have n processes running. If one of them says semWait, then some other process also says semWait. Whichever ones said semWait after the first one get blocked and have to go into that queue and wait for their turn to run. Meanwhile, the first one that executed semWait goes into the critical section, executes, potentially accesses and potentially modifies that file, And then when it's done, it says send signal, which allows one of the other waiting processes to run and also access that file. The following diagram will provide a way of visualizing what's happening here. Let's say we've initialized some values. We have S starting off at 1, and the number of processes will be 4. And so we have process 1, 2, 3, 4. We'll refer to these as A, B, C, and D. Now, this queue is not the semaphore queue. This is a queue of processes that are ready to execute. So the OS is managing these processes. All of them are ready to run. This one is at the front of the queue. So A gets moved onto the processor and gets to run. So we'll move that off of that. Processor. And it runs for a while. And because it's running, it's going to execute semWait. And that will cause the value of S to go from 1 down to 0. So S now equals 0. Now let's say that this critical section takes a while to run, and so A actually has a timeout. It gets booted off the processor before finishing its work, therefore before executing sem signal. So we have this queue of ready processes where A finishes, and it's going to go back to the end of this queue now, and S is now equal to 0. Now we also have a queue here, and this is the queue associated with the semaphore, which we've called Q. Now this is currently empty. There's nothing in here. But now that A has been booted off the processor, the next process in line is B. So we'll put B on the processor. B gets to run. Now B is running this same code. B will also execute semWait, except S equals 0 now. So when B executes semWait, the S goes down to -1, and because this is now negative, B is blocked. It goes onto this queue, and it must wait for its turn to run. So after B, which was removed from this ready queue, we have C and D, and each of them are going to execute this same code. So C will go on the processor. It will also execute semWait. That will cause it to get in line here. S will go down to -2. And similarly, D will also go on the processor. It'll also execute semWait. That will decrement S again, putting D here as well. So notice first that S, when it has a negative value, this value is the number of processes that are blocked and waiting inside this queue. So when S has a value of -3, it means that 3 blocked processes are in this queue. So finally, A gets to run again because all the other processes are blocked. So let me go ahead and clean this up. So A has just moved from the ready queue onto the processor. Now A was already in the middle of executing its critical section. Eventually it finishes and it executes sem signal. When A executes sem signal, that allows B to go from the semaphore queue back into the ready queue and increments S to be -2. Now after executing sem signal, A could time out. It could actually loop around and execute a semWait again, but let's say that it times out after this point. which puts it back on the ready queue, but after B. So this means that B now has a chance to run. And recall that the reason that B was in this semaphore queue in the first place was because it had just executed semWait. So when B gets placed back on the processor, it comes back in already having executed this. That means it gets to immediately go to its critical section. So B executes its critical section, and when it's finished with that, assuming it doesn't time out, it will execute sem signal, which will once again cause S to increment, this time to -1, which puts yet another process from this queue into the ready queue. And then let's say at some point B finishes, and it also goes back to the ready queue. So at a high level, that's how semaphores work. This is very basic code you might use to have multiple processes that do some sort of mutually exclusive operation. But we'll see a more complex example after we've talked about some other synchronization methods.